I guess we'll get started here. It's been about 10 minutes. I got it recording, so we will post that. All right, any questions about last week? I think definitely remember to, let's see, hold on a second. Make sure everybody here. Okay, so make sure everybody here, we only had finish the homework number 2, which really just is that you just have to log on to the assignment and click assignment, submit assignment twice. So make sure you guys do that just to get the credit. It's easy, you just put in the date, not too complicated. But definitely go over that that homework assignment, especially for the radar theory quizzes and tests that we'll have. That is a great study guide. So so definitely remember to go over that. And today we are going to be all about paper plotting and learning the first triangle. And then next week we'll do the second triangle. And then the week after that, we'll do multiple targets. So we're kind of doing baby steps on it, but we'll get used to it along the way. And we have lots and lots of practice problems. So if you guys use pencil, you can erase, sometimes use different quadrants of the plotting sheet. So you could use multiple ones that way. If you have a ton, you could just burn through them, whatever's good for you guys. That's about it for announcements from me. If we are ready, we can dive right in. Share screen. Okay. All right, just confirm we can see the PowerPoint, right? Good, okay. Okay, so today we're learning the paper plot. We kind of started going over it a little bit last week, but the basic 4 things that we're going to be working on today is direction of relative motion, speed of relative motion, and then closest point of approach and the time of the closest point of approach. So we're going to start to use, and I think on my reference sheet, there is a guide of acronyms, because we start using this DRM, CPA, TCPA, throwing out all these acronyms that can be very confusing, but I'll try to say what it actually is. So these are the 4 basic things that we're concerned about. And I'm actually gonna stop the share and show you that video again of my example. Let's see. Can you guys see the video? I don't think you can see the video. You can't see it. Maybe I share the whole screen. Share my whole screen. Share. Okay. Okay, can you see the video now? I can't see you guys, so somebody.
Yes, we can see it.
Okay. Okay, so this is on the simulator, and we could see we have little blips or little dots, and we don't really know what they are. We got little dots here, 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 and here. The lighter yellow behind it is what we call the trail, or it's kind of the history of where it was, where it was, where it was, where it was, and where it is now is the brighter section. So that's the trail, if you will. So when I push play here, we can see that these lines are basically what we're going to be plotting. This is in an ARPA mode right now, so it's plotted the lines for us, which is really nice. But in reality, it's or in this class, we are going to be plotting those lines. So I'm going to push play. So we can see different vectors. Okay, so I'm going to pause this one. So this right here is our relative vector. What happens relatively? So I'm right here. I'm headed this direction. So relatively speaking, this guy is going to pass behind us. This guy's also going to pass behind us. These ones here that don't have any history are actually not moving. So their relative motion is going to be opposite our course and speed, right? So it's just going to be opposite of us because it's going to pass right along our side. So this is the relative motion. And then I'll switch back, I'm sure, here to true motion. There we go, back to true motion. So with our true motion, it's what the contact's true course and speed is. And I have this vector set at 16 minutes. Now we're not going to have vectors set at 16 minutes. We don't have that capability on our plotting sheets, but we will create a vector basically at 6 minutes. So this is the true motion. So this helps us figure out what situation it is. Am I a giveaway vessel? Am I stand on? How can I figure out where they're going? And I definitely don't want to cross ahead of someone if I'm the giveaway vessel. When I go back to relative here, here's our relative. This helps us figure out where they're going to be if nobody changes their course and speed. So if I don't change my course and speed and they don't change their course and speed, this guy right here is going to get 1 mile from me. And so is this guy. They're both going to be about 1 mile from me about here. So that's the closest point of approach. That's our CPA, closest point of approach. So we can see that actually here. CPA is 4 miles for target number 10, which is this guy, target number 10. So we could see what his range and bearing, CPA, TCPA, its true course, its speed through the water. And then can anybody guess what BCR or BCT is? It's bow crossing range and bow crossing time. So when is it going to cross our bow, our heading? That's what we're looking at for the bow crossing. So we can see what its true vector is. And that's why I also like to keep the trails on, because the trails give a great indication of what their true vector is. And then relative motion really is an eye popper of, hey, this one's of concern. Its relative motion line is close to me. And this one's not much of concern because its relative motion line is going to be 5 miles away from me. I'm not too concerned with that. So the relative motion line is the quick way of deciding, hey, which contact or target here am I concerned with? So we see if no one changes what their courses or what their relative motion lines are. So that's why relative motion is so important. And that is basically what we're going to be doing today, is our relative motion lines. Let's see, I just let it play for a second. Okay. Let's escape out of that. Oh, there you are. Okay. Did that kind of make sense a little bit there?
Absolutely.
Okay.
I'm tracking.
Okay. Let's go back to the PowerPoint. Okay, so when our 4 basic plots, back in acronym land, we have the direction of relative motion. So that direction of relative motion, when we plot it, we can see, oh, is it close? Is it not close? But then we're also going to figure out what its actual direction of relative motion is. So we're going to have that measurement. And then we're going to have that speed of relative motion. Is this relative motion of this guy really, really fast, or is it really slow? Do I have some time to figure out, am I give way? Am I stand on? Do I have time, or do I need to figure this out really fast? What's that speed of relative motion? And then we have our CPA and our time of CPA. So again, that closest point of approach, and then our time of CPA. When is that going to happen? So I can help, so I know when it's happened, and then I know he will be getting further and further away of when that closest point actually happens. So those are our 4 basic things. Any questions with those? All right, let's go to the next one. So when we plot our first vector triangle, we're going to plot it on the radar plotting sheet. And if we were in the simulator, we would be looking, let's see, can I share this real quick? So we would be taking on or noting the range and bearing. So we would be using that EBL and VRM. Okay, pop quiz, what does an EBL stand for?
I'm not sure if you mentioned what EBL was tonight, because
I did not.
Okay, then I would have written it down, so I don't know what EBL means.
Okay, any guesses? What does the B stand for?
Bearing?
Bearing, yes.
Estimated bearing line?
Electronic bearing line. And then our VRM is our variable range marker. So let's go back to this guy.
Say that last one again. What was it?
Variable range marker. Okay. I'm kind of going all over the place with you guys here. Okay, this is back to the Canvas screen. But here we have 2 VRMs. So that VRM is the variable range marker. So here we have one at 7.4 miles, and here we have one at 6 miles. So we can make that ring change as far as we want. So in this case, we have an EBL measuring this raycon, and then that VRM is measuring its range. So we've got a range and a bearing from us, and then we take that information and we put it on the plotting sheet. So when we get our range and bearing, we want our bearing EBL line to be right in the middle of the blob. And then we want our range line to be on the closest edge of the blip. So that's where we want our VRM, the closest edge, and then our EBL in the middle of whatever blip it is. So we'll go back to this guy. So we want to figure out how to transfer what we see on our radar to our radar transfer plotting sheet and then plot those. Back in the old days, a lot of times, and I learned how to do this, and actually in the radar class, in the simulator class, they kind of did it with not exactly grease pencils, but they would use whiteboard markers on the screens. But sometime in the olden days, you would have a little grease pencil. Do you guys know what I mean by a grease pencil? It's like a...
No, I don't.
I'm old, I know what you mean.
A waterproof crayon basically that you can like wipe off of smooth surfaces. I want to say a lot of engineers use them on a ship to write on a pipe or something.
Okay, that sounds familiar.
And a lot of like whiteboard, if in the deck side, we'd use them on the ballast boards. Instead of the whiteboard, you would put in the grease pencil, like which tanks were empty, or I don't know. Anyways, it's kind of like a whiteboard, but it's not.
Yeah.
So because the radar screen, if it doesn't have an ARPA, it gives you what's happening at the moment. You want to have that history of what happened 6 minutes, 12 minutes, 10 minutes, however long ago, so you can plot this relative motion. So you would put a little blip where it is, and then wait for however long, and put another little blip where it is, and then you can create that relative motion line. So instead of doing that on the screen itself, we're going to do that on the paper. So it's important to get accurate measurements, right? To get actual or close EBL and VRM data, so we can put that range and bearing onto the plotting sheet. And unfortunately, I'm just going to give you that information for all of our questions here, but that's the way it goes. So we are going to also plot our own ship's vector, and that's our own course and speed. Plot our relative track, plot the contact's true speed. So after we plot the relative track, we're going to form a triangle to then plot and see what the contact's true course and true speed is doing, which that is going to help us decide, are we the giveaway or burden vessel, and what needs to happen in this situation. So finding the contract's true course and speed is important. And then we need to recognize what kind of situation it is, meaning crossing, meeting, overtaking, whatever it is. So tools that we're going to need are roll plotter. And most of you guys have roll plotters, right? That's what we're using. Sabrina, are you using a triangle or a parallel ruler?
I don't have any of those, but I will get those.
Okay. Yep.
So I'm unprepared. I'm sorry.
That's okay. Some sort of nav tool. But the roll plotter and the triangle are great. Calculator, most of us have that on our phones. And the dividers or compass. Divider is 2 pointy ends, and the compass is 1 pointy end, 1 pencil end. Oh, there we go. And the radar plotting sheets. You could also get the rules of the road book. If you don't have one, it's great to have one. And then the radar manual. You guys don't really need it in this. Well, I guess you guys are just looking at my PowerPoints for this class. But it's a great book to have if you're geeking out on radar. It's full of great information and lots more practice problems. So that's great.
Sabrina, it's on Amazon.
Cool. The actual radar plotting sheet. And then we're going to dive into that. So we kind of went over this a little bit at the end of class last week, but on our radar plotting sheet, we have the concentric circles, and those distances can change. So it can be, it goes with the scales on the side here, right? There's our distance scales. So if we are on the 3 mile scale, the center is 0 and the edge is 3. If we are on the 24 mile scale, center is 0, the edge is 24. So these are split up in sixths, essentially. So if it's 12 miles, which is the one that we're typically going to use. So typically we're using the 12-mile scale. And so we have each circle is 2 miles, 2, 4, 6, 8, 10, 12. So that's the typical one we're going to use. So that's just a quick way to figure out a distance really quickly. And on the actual radar, you can have these radar rings, is what we call them when they're displayed on the radar, a quick way to figure out what their distances are. Then we have our degrees around the plotting sheet. So we have north, east, south, west, just your kind of like a compass rose. In this case, we're just kind of assuming everything is true. We're not going to do any, you know, compass error or anything like that. So those are our degrees. And then we have our distance scales on the side. So we have the 24, 12, 6, and 3. On the newer, this is an older plotting sheet or an older PowerPoint, I guess. The distance, speed, time scale is on the bottom. And what I have on my side is a speed scale. We're not going to use that speed scale, and we're not going to use the distance, speed, time scale on the bottom. We're just going to use that distance scale on the side, and we're just going to use the one that we have decided to use, which is typically 12. Sometimes we'll do 6, sometimes we'll do 24, but I'm going to say 80% of the time we use the 12 scale. And then we're actually going to use our 60D street to figure out our speed and distance.
Captain, how does that logarithmic time speed distance scale work?
You know, I'm not really sure. There's a little direction down there. Do you see the little same divider spread? I don't really know. I honestly have not used it.
Yeah, I see what you're saying. Yeah, same divider spread. Well, yeah, okay.
Yeah. We are going to be doing things in the 6-minute or 12-minute time frame. So that makes our 60D street calculation super quick. Do you guys understand when I say 60D street? Do you have that in your
in coastal navigation?
Yeah.
I never heard it referred to 60D street. We just in captain school it was just DST.
DST.
Yeah, and it was a circle with a line drawn through it with a D and an S and a T. And the line had like an X signifying times, but it also had 2 dots signifying divide. So just whatever direction you went, it was the other thing.
Okay. I think I'm going to go do a little 60D street thing.
Okay.
Stand by. Let me open that up.
In fact, when I had that in Coastal Nav last semester, I felt like it was way more complicated than it needed to be, because if you just know the D and then the S and the T, it's really simple to work. If you got 2, then you have the third one.
Yes.
Yeah. I never heard it called 60D street though, but I like that.
A lot of places call it different things. I never called it 60D street, but the last place I taught at in Seattle, that's what they called it. And yeah, I just kind of adapt to what people are doing. Okay, so can you guys see a new PowerPoint? Speed, distance, time?
Yes.
Yes, okay. So units of measurement when we're talking about speed, distance, and time. Our distance is in nautical miles. A nautical mile is different than a statute mile, right? Everyone knows that. So our statute mile is a little bit less. Our nautical mile is 6076. I almost want, I don't have my globe. Okay, I'm gonna go to my PowerPoint or my whiteboard. Show all windows, there we go. Whoa, it got yellow, there we go. Okay, so we have the Earth, right? Here's the North Pole, here's the South Pole. And we have latitude. Here's our latitude, right? Our latitude is all parallel. Our longitude are not parallel, right? I know this is sloppy. But we start with our latitude at 0 degrees. That's the equator, right? That's our starting point. Longitude, what's our starting point?
Greenwich Mean Time?
Yeah, well, that is our starting point, but it's called something else.
Oh, Prime Meridian?
Prime meridian. Yes, so meridians, all longitudes are called meridians. The prime meridian is our 0. And then we go 180 degrees east and 180 degrees west. For the equator, we go, they're parallel. So we call our latitude lines parallels. So we have 180 degree range for longitude. For latitude, it can go from 0 up to 90. So if I was to measure this, maybe we call that 10 degrees. If I was to measure this, maybe we call that 40 degrees. So that means it's 40 degrees from the equator, and everything around it, that was a circle, is 40 degrees, right? So if we go all the way to the North Pole, that is 90 degrees. So our maximum scale is going to be 0 to 90 degrees. So that, now if we zoom in here, and we look at 1 degree, 1 single degree of latitude, and we split that up. What do we split up our degrees in, or how do we mark degrees? What is our position right now? What are we at? We're at like 41 degrees, 25.1 minutes north. Does everyone recognize how I wrote that out?
I do not.
Okay, so our latitude, I guess back to geometry, when we're talking about circles, we have 360 degrees in a circle. In each degree, we have 60 minutes. And in each minute, we have 60 seconds. So that has nothing to do with time. It's talking about the amount of arc, if you will, the amount of arc of a circle is when we have degrees, minutes, and seconds. Now, typically, we do not go all the way to seconds. We stay in minutes. We stay in degrees and minutes, and then tenths of a minute, which can be tricky because tenths of a minute, but if you guys are adding and subtracting time or adding and subtracting degrees, we know that 360 is as much as we can get. 60 minutes in 1 degree, so we can't have 75 minutes, if you will. We could only have a maximum of 60, and then it's 1 degree. So this is long story short here. We have 1 degree of of our 90 degrees of the Earth is split up into 60 minutes. 1 minute is equal to 1 nautical mile. That is where the nautical mile came from, or the nautical mile was invented, if you will. I don't know where the statute mile came from. I don't know, Americans just like to do things differently. But the nautical mile.
It had something to do with Greece, actually.
Greece?
It was something the Greeks came up with. And it was the distance from one palace to like the Parthenon or something.
I don't know. But nautical mile is 1 minute of a degree of latitude. And our degrees of latitude are the same distance because these are all parallel to one another. Where the difference between longitude here is going to be a lot different than the distance between 1 degree of longitude up there. So our longitude doesn't give us a distance scale, where our latitude is all parallel to one another. So that 1 degree of latitude has 60 minutes in it, and 1 minute is equal to 1 nautical mile. So that's why on our chart, if we are measuring distance, we can use our latitude scale to measure 1 nautical mile is 1 minute. So here's 15 minutes, here's 20 minutes. So there's 5 minutes in between. This would be 1 minute, also equal to 1 nautical mile.
But it's kind of like the minute thing is a misnomer. It's like 1 degree holds 60 notches, and each notch holds 60 baby notches, you know?
Yes.
Does that make sense? Yeah. So yes. Sabrina, don't let the minute thing throw you.
It's nothing to do with time. It's
nothing to do with time.
It's a like, measure of an arc.
So like say, so say 1 degree is a degree. And then if you break it down, that degree has 60 individual notches, we'll call it.
Okay. I appreciate it, Captain Kevin, but I don't want to get confused with 2 people.
Okay.
But thank you. But Captain Bree, I think where I'm a little bit confused is in that box where it says 40, and I don't mean to cut you off, 41 degrees and then 25.1. Where are you getting that specific right now, like on your picture where you're like, we are at, like when you had just said 5 minutes ago, when you're like, we are at 41, like, where are you getting that number? Like, did you put a spot on that map and then?
No, I just made that number up because I was plotting on this chart, and this is 41.20, and I was plotting at 41.25. Okay. So it was just in my head because that's like, what
I'm like, I don't know, where is she getting that number? Okay.
No, that's just I don't know if you could see on the chart. It says 41 degrees, 10 minutes, and 20.25.
Okay.
I was doing something for my other class. And
okay. Okay, cool. But keep going. That was the part where I was confused. I'm like, where is she getting that 25.1? I don't know.
It's just an example of how we write our latitude and longitude.
I see. Okay.
Okay. So let me go back to this guy. Okay. So distance. We have 1 nautical mile, or we have our distance in nautical miles. Time, we have in hours or minutes. It can't be both. So that is a tricky thing. We have to convert when we're doing our distance time speed calculations to all hours or all minutes. So it can be 75 hours, or excuse me, 75 minutes or 1.25 hours, right? A quarter of an hour. So it can be all in hours or all in minutes. It can't be in both. And then we use our speed, which is what we call, our nickname of speed is knots. Now, technically speaking, a knot is a nautical mile per hour. So instead of using that, mph, that's going to be our statute miles per hour. Our nautical miles per hour is a knot. So that's where the fancy term of knot came from, just nautical miles per hour. Now, when we put it into a formula, for those of you who like formulas, we have distance equals our speed times our time. Now, if we want to use minutes, which for minutes, I'm going to say most recreational boaters are going to use the minute time. So we'll have a 60. This is kind of our conversion number that we put in here. So we have 60 D Street. That's why I keep saying 60 D Street. So 60 times distance equals speed times time. And that time is going to be in minutes. So if we're looking for speed, we do our calculation, we have speed, and it's going to be distance, nautical miles, per time, per hour. So that's where we get our equation of nautical miles per hour speed, but our 60 D Street. So we're just getting one of these alone, that you could move around that equation. Okay, I'm going to skip through this. And then Captain Kevin was talking about the magic circle. For my magic circle, I have the 60 in it so that we can use time and the minutes instead of hours. And for the magic circle, we multiply across and divide by the bottom. If we just have one missing thing, that's fine. So let's see here. We're missing our distance here. So we multiply from the bottom and then divide from the top. Okay, I'm not planning on going through all of this today. So that is not our PowerPoint, but that is a quick how speed, distance, and time are kind of related to one another.
Can I ask you a question, Captain Bree, before
Yes.
you move on? And I've never learned that yet in any of my classes. So thanks for explaining that to me. Is the reason why they use 60 D Street or 60 DST, because you said because of mostly it's measured in minutes as opposed to hours? Because I saw there was two formulas. One was just
Yes.
T equals S times T. So is that where 60 DST, or like the slang of 60 D Street?
Yeah, so 60 D Street is going to be where your time is in minutes, and that's typically used for shorter distances, where if you are calculating the minutes that it takes you to get from Newport to Hawaii, you're going to have this astronomical number, right, in minutes. But if you do it in hours, then it's just a little bit more friendly to work with. And a lot of times in the commercial industry, mariners, we put everything in the 6 minutes. So 54, 42, everything in that has a multiple of 6, so that we can do those hour calculations really easily, because we put everything into hours instead of minutes. So it's just a more manageable number to look at. But typically, if you're just going to go from, Long Beach to Newport or whatever, our 60 D Street calculations are so small that we just use the minutes, and so we have that 60 in front of it.
So you would just use D equals S times T if you're going from Newport to Hawaii.
If you're going to use the T in hours, it's just D equals ST.
Okay, great.
T's in hours. 60 D equals ST is T's in minutes.
Got it.
So kind of just depending, you can go back and forth, but
depends on what is the variable of T, if it is minutes or hours. I see.
And a lot of times, however an individual learns it, that's how they're going to do it. And they're going to convert all of those minutes to hours at some other point, or they're going to just convert always minutes to hours.
Okay. Thank you for explaining.
Yeah. Okay. Let me stop this real quick. Okay. Sorry. Ooh, where did that one go? Okay, so I think I'm on this one. Okay, so in our class here, we are going to be labeling what we mark on our transfer sheet. So we kind of just went over our transfer sheet. We are going to have labels for each little blip that we put on. So just like if you put something on the chart, you should be labeling it. So that way, if someone else comes up to the chart, they don't just see a bunch of lines and dots and trying to figure out what was in your head, right? We always want to label things clearly. So our labels, for the first little blip that we put down, we're going to call that one R. I did not come up with these. I don't know why it's called R, but in a minute, I'll give you little memory aids here. And then the next blip that happens, and we're going to try to do it every 6 minutes, we call M. And if we connect those two lines, we get a relative motion line. So our R to M is relative motion. And when we draw that all the way out, we get a relative motion line. So that's our RML, relative motion line. So that's if no one changes course and speed, that target or that little blip is going to follow along that relative motion line. So it's going to get very close to us. Now, the next point of the triangle that we're going to add is going to be our own information. So we don't know what that vessel is doing. We just know that relatively from us, it had a range and bearing at one time. So we put the little R, and then 6 minutes later, it had another range and bearing, and we put another little blip and we labeled it M. And then the other piece of information that we know is what our course and speed is. And so we're going to create an E of what our course and speed is. So E to R is our own ship, or for some reason I used to call it Earth, but that doesn't really make sense either. ER is to us. And if you look at the very bottom of your radar plotting sheet, it will tell you E to R, R to M, and E to M. Can you guys see that? E to M is them, right? THEM. What are they doing? E to M. Let's look at that in a bigger triangle. So we have, it's made up of 3 individual vectors. The R to M is the relative motion. And if we measure the distance between R and M, then we can calculate what the speed is, right? Using that 60D street. So if we know a distance, what we get from here and what we get from our radar is a distance, and then we convert that distance to speed. So we get our direction of relative motion and our speed of relative motion. Our E to R is our own ship. So the origin of all true vectors is going to be the E, but E to R is our own ship's course and speed.
Now, aren't we in the center of that plotting sheet though, the little cross?
Yes, we are. So we have to create our own ship's vector on the relative motion vector in order to create this vector triangle.
Okay, thank you.
So we're going to be paralleling and creating, just creating that third line of the triangle so that we can calculate this information. And then E to M is going to be their course and speed. So what do we have here? The first thing that you plot is going to be your R. And then we can plot our M, which is what happened typically 6 minutes later. And then we could plot our E, which is going to be from us. Now, if we're doing this on the radar in class in a simulator or out at sea, we have to wait that 6 minutes from plotting R to plotting M, because we have to wait for that little blip to move across the screen. Now, 6 minutes is a long time. So in that 6 minutes, we can plot our own true course, our own ship's vector. So it doesn't really matter what order you do it in this class, whatever makes sense to you. We're going to be practicing it tonight. Let's see. I want to take a quick break here.
Can I ask you a question again before we
Yes.
take a break? I understand from R to M it's 6 minutes later, but being that E to R is our own ship and E to M is them, what are they doing? But what does R to M mean? But is it just the 6 minutes thing, or is there something else?
R to M is relative motion.
Okay.
So here,
Just for my own benefit, when you say relative motion, you mean the relative motion of that other ship and the direction, the bearing it's going, giving us that relative motion line.
yes. So let's go back real quick to this one.
I need that break too, though.
Okay. So here we have our true vectors, and there we have our relative motion lines. So our relative motion, if we stay on our course and speed, that vessel, this blip here, is going to travel blip, 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 all the way across the screen like that. If we continue to our course and speed and they continue their course and speed. Now, relative motion is a hard, sometimes is a hard thing to conceptualize, but your brain does it automatically all day long. That's what makes it so when you're walking in a mall, you're not bumping into people, right? That you can see that someone is, maybe they're not walking in the same direction as you, maybe they're walking, crossing whatever way, but relatively, are they getting closer to you? Even though they might not be facing you, you avoid them, right? So it happens in your brain kind of without thinking about it. And now we're going to put it on paper, which is harder to conceptualize. But this relative motion, it happens in everyday life of how things are, multiple things are all moving around. And if they're not hitting each other, they're trying to avoid each other. And they're using relative motion to do that.
Thank you. And that blue screen, or when you brought that up, that like all made sense. Like the yellow, that all made sense. I think, I know we're going to take a break, but like the whole triangle thing, I think that makes sense. But then because there's not triangles on the blue thing, I think that's where I'm getting a little, but I think it'll all make sense.
It'll come together.
Yes, I believe in that.
All right, let's take a 10-minute break here.
Okay, I'll go print off those pages.
All right, cool.
If Captain Bree is back, I have another question, of course, but I don't know if she's back yet.
What's up?
So I got the papers. I was able to print them. On the course materials, I just want to make sure that I purchased the correct things. The materials that we need, are those like specific? Sorry, I'm trying to go to where it says that the
Yeah,
things we need course materials.
See what I
So,
wrote.
like, what's that?
I'll go to it too so I can see what I
Okay.
wrote here.
It says like Weems and Plath ultralight divider, because I started looking on Amazon, but I don't want to like purchase like the wrong protractor. So are these like these are like the types that we need?
Yes, so let me show you here.
Okay.
Um,
And I have an idea of like what they look like. And we've used like the rolling protractor or whatever in boat handling when we charted our courses. So I've seen them. I just want to make sure I don't purchase the wrong thing.
So we need a tool to measure, so we kind of look at this part, to measure distance is dividers or compass. And so what I put on the thing, the Weems and Plath, whatever, Weems and Plath ultralight dividers 176 is interchangeable. So you could change out, instead of having two pointy ends, you could change out one for a pencil.
I see.
So that's why that one's recommended. But
Okay.
if you were, borrowing a friends or families and all they had was a compass or all they had was dividers,
Okay.
just a tool to measure distance. Either a compass or dividers. The recommended one is a combo one that is sold at the bookstore. That's the only one we sell. But Amazon and also West Marine has dividers as well.
Oh, okay.
And then you need something to measure course bearing azimuth angles, something to measure angles. So you can use triangles, you can use the parallel rulers or the roll plotter. You don't need all three of these. You just need something to measure angles. So whatever you're most comfortable with. If you've used the roll plotter before, that's a great one. And then a calculator and a sharp pencil.
Okay, so going back to the top, we just need one of those, or do we also need a compass too? Like a divider compass?
Nope, you just need a tool to measure distance.
Okay.
And here you just need one of these three things.
Got it.
So we need something to measure angles and something to measure distance. So we're going to be plotting our, range and bearing. That's a degree and a distance. You need a tool to plot both of those. And if you go here, I have a little YouTube video explanation on using each one. So if you want to figure out, I don't know, which one to buy if you're buying new ones, you might check that out. But yeah, okay. So Louise asked, do triangles differ from protractors? Yes. Triangles are, these are nautical, used for, I guess, nautical purposes. But they are sold at West Marine, Amazon, the bookstore. If you guys are up in Long Beach, SafeNav has everything. They have all the charts as well. It's a pretty cool store.
What was the name of that store?
I'm trying to think, down in Newport. SafeNav. I think it's off of 6th Street downtown. Is it there like Mimi's or something in Newport? I don't know where else.
Minis Yacht Supply.
They probably have some nav tools as well. But I like teaching the class in person because I have all of them and I have everyone practice how to use every single one. And then they figure out like, oh, I like the triangles, or, oh, I like the roll plotter or whatever. So, but it's too much of an investment to buy them all. Anyways, a protractor is different than a triangle. they do have kind of the same features, but the triangle is built so we can parallel things very easily, where a protractor doesn't really parallel a line. So that was my answer to that. Let's see. Okay, let's continue on our PowerPoint. If I can find it. Okay, so our vector triangle, we plot the R. 6 minutes later, we plot the M. The E is the origin for all true vectors, and how we plot that E is by plotting E to R, which is our own ship's vector. So our own ship's course and speed, which we convert to distance to plot. And that's where we get the 3 points of the triangle. The 3 points give us the 3 legs to the triangle. R to M is our relative motion vector. E to M is the contact's true course and speed. E to R is our own ship's course and speed. So that E is the origin of all the true course and speeds, where R to M is the relative motion. We have our big long list of what we are going to learn today. So our own ship, OC, I guess you could just call your own ship's course line. I always like to put in kind of our heading flasher. Like on the radar screen, we'll have a line of where our heading is pointing. So that's one of the first steps when we're plotting, is to plot where our heading line is. And then we're going to plot the contact's first mark, which is R. Then we're going to plot M, which is the contact's second mark. And then we're going to plot E, which is we use our own ship's vector to plot where E is, and that's our origin point for all the true vectors. So we can create that triangle and get that information. So each line, so our R to M is going to have a direction and a speed. Now, we're down here, it says direction, right? Direction of relative motion line, those are the same. Our new relative motion line. So we're not going to get into that tonight, but that is going to be tomorrow or next week when we talk about collision avoidance. And we want to basically bend that relative motion line so that it will not get too close to us. And how do we do that? So that new relative motion line is going to be what we're going to talk about next week. Today, we're going to talk about the closest point of approach. So that CPA is going to be very important. And a quick way to measure CPA is to measure it at a 90-degree angle from your relative motion line. Now, you share. My whiteboard's really dark today for some reason. Okay, so here's our circle, right? If we have, I guess we're doing a lot of examples like this. We have a blip and a blip, so we connect those blips and we get our relative motion line, right? Now our CPA is how close does that, what is the closest point of approach? So if my heading, let's do this. If my heading is due north, that's where I'm headed. This point here would be that bow crossing. So that's where it's going to cross my bow if that's where I'm headed. But it's not going to be its closest point of approach. If I'm looking at distances, this distance is further than, say, this distance. The closest that vessel gets to me is going to be, you know, it's however far, probably about right here, and then it gets further and further away. So this point is called the CPA. Now, and how you get that is basically a tangent circle. This is a circle where this is that VRM, if you will, and where it touches that VRM, or kind of a circle around us, is going to be our closest possible point. Now, the quick way to measure that is a 90-degree angle from your relative motion line. So if we use our triangle, which has a 90-degree measurement on it, we can plot, I guess in this case, that would be my, so this is a 90-degree angle where we're going to find the closest possible point to where it hits our cell, gets closest to the us. Does that make sense? Okay. Okay, so let me go back. So we're going to measure 90 degrees from our relative motion line is where our CPA is. And we're going to get the direction and the distance. So we're basically getting the bearing and the range of where that CPA is going to be. How close is it going to be, and what bearing will it be? I don't know, convert that into more useful information in our heads. You know, are they going to pass ahead of us or behind us? And how close is basically what we want to know. But what we're going to actually measure is that bearing of the CPA and that distance. Then we have MX, and that's going to be what we're going to talk about next week as well. That's the point of execution. So that means what point are we going to execute our maneuver? So if we are the give-way vessel and we're going to turn, we don't have to turn when the guy's 10 miles out and we have a constant bearing relative motion, you know, a 0 CPA. You don't have to actually change course until basically whenever the captain wants to, whatever is safe for you guys, and it's going to be given to us in our problems. But you don't have to, you know, avoid him 10 miles out. You can have a point of execution of when you're going, when that vessel is so far, that's when we're going to bend our relative motion line and alter course, basically, or speed. And after we alter course or speed, we're going to have a new own ship's true course and a new contact's relative motion line. That's where we get that R prime, if you will, or R to the first. That sometimes it's just like a little tick next to the R, but it's kind of like the new R. We are going to change. So we're changing that R to change the whole triangle. But don't worry about that too much this week. That's all going to be next week, okay? So this week, we're just focusing on that relative motion line, then finishing the triangle to figure out what the other contact's true course and speed is. So then we could figure out, excuse me, are we the burdened vessel? Are we the give way vessel? So, okay, are we ready for Captain Ron's animation? So in this, let me explain it before it gets all animated on us. Here we have the center of the chart, and we have our own ship's vector, our own course. We have a contact off our starboard beam pretty much, and we've plotted its little blip at whatever time it was. Then we have to wait 6 minutes to plot another little blip. So in that 6 minutes, we're going to transfer over our own ship's line. So first blip there we call R. Then we parallel over our own ship's line, and we call that E. As this 6 minutes are passing by while we're doing this, then 6 minutes happens, and we put a mark, and we call that M. Now we have 3 points to our triangle. So we're going to create the lines or the vectors. So R to M is relative motion, and you extend out that relative motion line. So where is that relative motion? Where are they going to pass? They're going to pass behind us. There's no actual scale, so I don't know how far. Yes?
How did you get that point for the E? Like, was there a given distance that you placed it, or it was just random, but it had to be parallel?
No, not random. It is my own ship's vector, meaning my course and my speed.
Oh,
so
okay.
how fast am I going? I'm going to convert that with 60 D Street in that same time scale. So if I know I'm going to do this in a half hour, then I'll use a half hour. We're going to use 6 minutes. So how far am I going to travel in 6 minutes? That's going to be how far away R to E is.
Gotcha.
Right?
Okay.
And we always want to think about it's E to R, that's the direction of our true. So, if we're headed south, our E is going to be up here because it goes E to R is our own ship's course, E to
Gotcha.
R. So then we plotted the M and we created that relative motion line. If we go E to M, that is their course. So they are actually headed, northwest. We are headed north, but they are going to pass behind us. So we can figure out, if a risk of collision situation is apparent, then who is the giveaway and burdened vessel? That true course of what they are doing is going to help with that. If we're looking back at our relative motion line, the closest point on the relative motion line to us, how closest point of approach, CPA, how close are they going to get? So they're far away, far away, far away, as close as they can possibly get, far away, far away, far away. And how we measure that is 90-degree angle from the relative motion line, that 90-degree angle. Or
so is everything happening in that triangle actually happening behind where the center is?
I'm not following your question.
So the REM triangle that you've plotted out is actually going to transpire in 6 minutes where the CPA is, relatively?
So as we plot this, it's kind of old news, if you will,
Okay.
right? Because we plotted the R, that was 6 minutes ago. It's the M, and then as we're finishing this, the M is continuing down the line, right? If we have not changed course and they have not changed course, it's going to continue down our relative motion line. So from there, we're going to find like how far away are we going to, be comfortable with our execution and so forth. And how close is it? What is our minimum CPA? So we're using this information to then project out how we want to handle the situation. So we're helping that situational awareness.
I guess I'm still not understanding how the E got to where it is based on your speed and bearing. How you placed it behind that R.
Okay. I'm going to say hold that thought because I think it will make a lot more sense when we do this with numbers.
Okay, cool. Thank you.
And we do this with, yeah, data. Okay. We are almost done with our PowerPoint here. Constant bearing, decreasing range. Has anyone heard of that before? Okay, so CBDR, constant bearing. If something is on a constant bearing and decreasing range, that means there is a risk of collision. And that's what the rules of the road says. So if something isn't changing bearings and it's getting closer and closer, it's relative that there can be a collision. If its bearing is constantly changing one way or constantly changing another way, then there is no risk of collision there. So that constant bearing, decreasing range is where we're going to get that that risk of collision. Okay, relative motion is what runs you over, right? So even if you're like, that guy's not pointed towards me, you know, he's pointed one way, I'm pointing the other, we'll be fine. The relative motion is different. So that's where we can be deceiving. If I'm, you know, walking this way or you're driving this way and I'm driving this way, relative motion wise, we could be leading to a collision. So our relative motion avoids our collision avoidance, helps us with navigation and situational awareness. Navigation, I wouldn't really say relative motion helps our navigation too much. It's more of our true motion because what we navigate off of are typically not moving. So that's a little weird, but anyways. Okay, I'm gonna skip that. I think we've done this. I want to do an example. I feel like I've said this a million times now. R to M, relative motion, E to R, your own ship, E to M, them, the true motion. Okay, so I did want to go over this real quick. This is kind of our grading scale. So as we do these, the answers will be on the back page. And for your relative motion direction, plus or minus 10 degrees, CPA plus or minus half a mile, speed plus or minus 3 knots, time of CPA plus or minus 3 minutes, direction 10 degrees. So just keep that in mind as we are plotting. If you don't get the answer exactly, it can be lots of things. It can be, you know, how comfortable are you with the plotting tools? It can be, you know, the thickness of your pencil. It can be all sorts of different little things. So you want to be as accurate as possible, yes. But if you are a little bit off, try not to get too frustrated with it. Give yourself a little bit of grace there. Okay. Okay, I guess this is an example here on the computer. We'll go over this one before we dive into our own. So here they told us we are relative motion north up. We are in the 12-mile range with 2-mile range rings. Our own course and speed is true north course with a speed of 20 knots. Draw and label your own ship. So we always want to draw our heading line, which they didn't draw our actual heading line. They just put our own vector there, which shouldn't be labeled R. I guess this is a little confusing here. Don't look at the labels. They put in our own vector. So in 6 minutes, we are going to be moving 2 miles. So that's why we use the 6-minute number, because 6 minutes is 1/10 of an hour. So when you do your 60D street, you literally just move the decimal place over 1. So in 6 minutes at 20 knots, we would travel 2 nautical miles. Our range ring is 2 nautical miles. So my distance in my 6 minutes would be 2 nautical miles in the direction of north. Now my step 1 is to plot our first little blip on the screen at minute 0. During that 6 minutes of wait time, I can transfer my own plotting, my own ship's vector, parallel it over to the R. Oh, I understand. T is used in some books, so you might see that around, but on your plotting sheet and in most of the books, it's an E. I understand that can be confusing, but switch out this T. So here's our R, that first blip, and in the first 6 minutes, we've now plotted our E. So ignore the T, it's an E. And that's where we get our E to R line, is our own ship's line. Then 6 minutes later, our blip moved. And so we can plot that and call it M. So now we have E, R, and M. And now we have a triangle. We can connect all these lines and create vectors. We draw a big line from R to M, and we get our CPA. We draw our E to M, which is them, and we get the target's true course and speed. And then if we have this case, maneuver when they are 5 miles away, this is our MX. If we wanted to keep a 2-mile CPA, we would draw our relative motion line, our RML, bending it from our MX to a tangent, our given CPA. But that's what we're going to do next week. Okay.
Can I ask you a quick question? Hopefully it's quick. I'm sorry to always bust in. M, how do you know that M, I understand E and like moving, like I understand that. How do you know that R, that blip, you know, is going to be moving to where M is? I understand 6 minutes, but how do you know that they were going that direction and not, you know, like let's say the blip was here and going across? Like, how did you know that M would be going at that angle?
I didn't know.
It's just an example.
Yes, it could have been not moving at all. It could have been moving away from me. You know, increasing distance. It's wherever that blip has moved in 6 minutes.
Okay.
We typically, every radar class that I've taught, they always teach it as like imagining it, you're going north and you have someone on your starboard side crossing. Okay. Because that's the situation that you have to give way to them. And when you're heading north, it's a little easier to visualize. Now we're going to do lots of practices tonight. So there are going to be different scenarios, but I understand the PowerPoint really just showed the one.
No, and that it makes sense. I didn't know if that, like, I was like, why is M always like, anytime you brought up,
it's not always there.
That same thought. So I'm like, what?
No, it's not always there. If it's there, that's typically a situation that's like, hey, red flag, I'm the burdened vessel. I need to do something. Okay. I need to change course or change speed.
Okay, thank you.
Okay. On Canvas, I put in some in-class practice problems. I don't know if you guys saw that, but that's what I'm going to be working off of. So I will, you know, write it on my whiteboard, or I'm actually going to write it not on my whiteboard, on the transfer sheets. But if you wanted to follow along with the numbers, they are on that that Canvas. For under PowerPoints, there's the PowerPoint and then the in-class practice. Okay. So we are going to start with our relative. Is this on? Can you see the screen? I don't think so. There we go. That's better. Okay. So we're going to start with our relative motion problems, and then we're going to do our first triangle, the whole set. So let's plot number one. So number one tells us at 5:05, we have a range and bearing. There we go. So at 5:05, we have a bearing and a range of our little blip. And then 6 minutes later, we have a bearing and a range of the same blip. That's what this information means. So we want to plot the relative motion line. So we get our direction of relative motion, our speed of relative motion, our CPA, and our time of CPA. We can get all of that information from just that information. Okay, so let's plot that. I will use the roll plotter. I think that's what most of you guys use. So our first one is bearing 043. So we're going to find 043. So here's 043 at 10.3 miles. So I'm going to use the 12-mile scale. It's going to be somewhere in between those. And then I'm going to use this 12-mile scale here. So circle it, which one we're using. And we're going to find 10.3. Okay, so I see how I have 0 all the way to 10.3. I have 10.3. And then I start from the center here, and I'm going to swing my little arc. So right here is R. I'm going to erase a little bit so it's not as confusing. So I've marked my R. Then it gives me my next time, 6 minutes later. So this was at 05:05. I'll write the time there. 6 minutes later, we have a bearing of 4.2. And this is at 7.4. So it is less than 8. So somewhere over there.
What does the 7.4 mean again? What is that?
That's the range, 7.4 miles away from me.
From, oh yes, okay, thank you.
So I'll find 7.4. There we go, 7.4. And I have 7 point, put it on our scale. So this is M. Clean it up a little bit. And M happened at 05:11. So I have an R and an M. Now to create our relative motion line, we connect those two. We just connect R and M. So this is my relative motion line. So now I want to figure out what my direction of relative motion is and my speed of relative motion. I can't write. So when you're using this plotting sheet, this line gets so close to the edge, it is very strong, I don't know, urge to just say, this is my relative motion, my direction of relative motion. Don't do that. We always have to parallel this line back to the center in order to get a degree of it. So even if the line is up here, we always bring it down to the center in order to measure the actual degrees of that line. So we parallel this line. So I just put the line on the black line of my parallel plotter, and then you push down on the metal bar, and you can parallel it anywhere you want it. So I'm going to parallel it from the center. And now I get what its actual degrees is right here. So that would be direction of 2 to 5 degrees is my direction of relative motion. Now I need to figure out my speed of relative motion. So how do we do speed?
So you're going to measure the distance between R and M, and then hold up your pointer, your compass, against your length, and then do 60 D Street.
Bingo. So I see the distance between R and M. I can measure that distance. I got about 2.9. You guys see that? 2.9. So my distance here was 2.9 nautical miles. Now, my distance is 2.9. My time is 6 minutes. What is my speed? Did you get it, Captain Kevin? So if we use our, let's practice our 60 D Street magic circle. D is 2.9. Speed is our question mark. Time is 6 minutes. The two things that we have, we multiply and then divide by the other.
Is it 29? Oh,
Yes. 60 times 2.9 divided by 6 gives us 29. Our speed is 29 knots. So that's 6 minutes. We just move that decimal over from 2.9 to 29.
I moved it the wrong way, so we are only going 0.29 knots.
Okay. So you're always going to do that common sense check, right? That, hey, does this make sense?
Yeah, then that was like, duh.
So that's why we do the 6 minutes. So it's an easy conversion. But sometimes it's not going to be 6 minutes, right? Sometimes maybe you know, we're looking down and it was 8 minutes later that you remembered to plot the M or something. So you can just go back to that 60 D Street. Or wait until it's 12 minutes and then it's, you know, 2 times that. Okay, so that is our relative motion line, 225 at a speed of 29 knots. Now, what is our next one we're going to find is CPA and TCPA. So that's our closest point of approach and the time of the closest point of approach. So when is that going to happen? So our closest point of approach quick way to do that is do the 90 degrees from your relative motion line. So I like using the triangle because it has this 90-degree line already on it. So it makes this quick and easy. So I put that 90-degree line, I put my pencil in the center, and I draw a line. So this is my CPA. If I'm looking for my direction of CPA, it's already from the center. So I could say my direction of CPA is 315 degrees. And my distance of CPA, I'm going to measure that distance from me to that CPA point. Go over to distance. At 0.5 nautical miles. So that's my CPA. Now I want to figure out what time my CPA is. How are we going to do that? Going to think outside the box. It's not thinking outside. This is how you do it. So we know our relative motion line is this far, right? I just measured my relative motion, R to M. And that was 6 minutes. So the quick way to do this is to just continue every 6 minutes. So I know that was a light mark here. At this point, if this was 5:05, this was 5:11, 6 minutes later, this is going to be 5:17. 6 minutes later, this is going to be 5:23. 6 minutes later, this is going to be 5:29. 6 minutes later, 5:35, et cetera, et cetera. So if our speed of relative motion, we don't change, they don't change. We've just kind of plotted out the timing of this. So this is where, what is our time of CPA is plus or minus 3 minutes. So when we're looking at our grading scale. So in this case, I would say that our CPA is pretty much halfway in between. So I'm going to call my time of CPA 05:26. 3 minutes one way, 3 minutes the other way. You know, maybe if it was over here, 2 minutes, but your I don't know, your wiggle room here is 3 minutes. So that gives you a pretty good wiggle room. So my time of CPA, I'm going to call it 05:26. So with just this little information, we figured out all of these things without even plotting E. How you guys doing on that so far?
Good. That makes all sense. I forgot about E until you just brought it up.
I was wondering about E, but then I was like, I don't think I need to worry about it.
So we're gonna master R to M in 4 questions, and then we're gonna do some E's. So if we had our own, we don't even have on this examples here, our own ship's course and speed. But if we had that, we could plot E, and then in addition to these, we can get the target's true course and the target's true speed. So we can get all of this information without E. And then if we have E, we can get 2 more things: the target's true course and the target's true speed. Okay, Let's do the next one. Okay. Here we have 10 o'clock and 10:06, 100 degrees at 10.8, 99 degrees at 9.4. So let's plot those. So we have 100 degrees at 10.8, so that's going to be somewhere over here. There's our 10.8. So what do we label this one?
R.
R. Our first blip, we label R. Then our second blip was at 99. I feel like this so it's easier for me to see. 99 at 9.4. It's going to be and what do we label this one?
M.
M. Clean up a little bit. Okay, so this was at 10 o'clock and this was at 10:06. So we have an R and an M. Now we connect those lines. R to M gives us our relative motion line. So we want to figure out what our direction of relative motion and our speed of relative motion is. To figure out our direction, we have to parallel this relative motion line. I guess I'll use it. I feel like I'm a little off on my dots, but that's okay. Give or take, what is it? 10 degrees. Okay, so I got a relative motion degrees of 285. Direction of relative motion, 285. Now I'm going to get my speed of relative motion. So I get the distance between R and M. And my distance is 1.4. So I quickly convert 1.4 nautical miles to a speed of 14 knots. Using that quick, you can do the whole 60 DC, or we know that it's 6 minutes, so you just move that decimal place over once.
Couldn't you just subtract 10.8 from 9.4, which are the two blips that were given on the...
So that will work only if it's a constant bearing. This bearing changed a little bit, so it's not exactly that distance.
Okay.
Like if it was still, what was this one? 9.4, but it was over here at 9.4, that's going to be a lot longer, right? Than if it was right there. So it's very, very small when you're only talking about 1 degree of difference, but it just won't always be like that. So it's best to actually measure it.
Okay.
What's next? CPA. CPA, we do our 90 degrees, our relative motion line. So here is my CPA. My bearing of CPA is going to be 0.15. And my time of CPA, I need to figure that out. So I get my relative motion. Oops, I didn't do my, excuse me, my distance of CPA. Forgot that. So bearing of CPA was 0.15. My distance of CPA from me to my closest point of approach, 0.9. So 0.9 nautical miles is my CPA. My time of CPA, there's 6 minutes. Okay, I'm gonna have a lot more lines here. So we have 0, 6, so this would be 12. This would be 18, 24, 30, 36, 42, 48, 54. So I'm right in between my 42 and my 48. So I might call that 10:45. The answer calls it 10:46. They said I was a little bit closer to the 8 than the 42. I can see that. But again, you're plus or minus 3 minutes. So you'll be fine here. Yeah. Making sense so far?
Yes.
Okay. Let's do another one. Okay, so we have 1822 and 1828, 5.4 at 10 miles, and 5.3 at 7.9. So 0.54 at 10 and 0.53 at 7.9. Okay, you can see I didn't get my distance because it was 10 even. And I know on the 12-mile scale, where it crosses this circle here is a 10. So this is 10, 8, 6, 4, 2, 0, right? On my distance scale. So when I draw my little lines, instead of drawing big lines, I kind of am, guessing it in my head. This was exactly 10. This was 7.9. So I drew my line from 8 a little bit less because it's going to be a little bit less than 8, right? 7.9. So I didn't have to draw big, long lines. The more lines you get, especially when we do our second triangle or multiple targets, it can be like, why are there so many lines? This is so confusing. So the neater you are from the start, the easier it will be for you. But I just wanted to explain that real quick. So our 10, it crossed at exactly 10. We label that R. And this was at 1822. And then we need 7.9. Wow, I did that almost exactly 7 point. Like it when that happens. Okay, from us, 7.9. So right here is going to be our M. And that was at 1828. Let me erase that real quick. So we have our R and our M. We connect R to M. And we get our relative motion line. We want to know the direction and the speed of our relative motion line. So we always parallel our relative motion line back to the center to get our degrees. So here we have 2, 3, 8. Our direction of relative motion is 2, 3, 8 degrees. Our speed of relative motion is going to be 2.2. So my distance here is 2.2 nautical miles. We know it's 6 minutes, so we move that over and we call our speed of relative motion 22 knots. Then we want to know what our CPA and our time of CPA. So I use the 90-degree over our relative motion line. Okay, I moved that triangle a little bit. There we go. Okay, so my CPA is going to be at a direction of 328 degrees at a distance of 0.8 nautical miles. Then we have to figure out time, TCPA. So that's our 6 minutes. Now we just walk our dividers, our compass, whatever you guys are using. Okay, so we have 22, 28 plus 6 gives us 34, plus 6 gives us 40, 46, 52. So we're in between 46 and 52. And I would say we're leaning on the closer side of 52. So I might call this 1850 is our TCPA. All right. Any questions on number 3? We're going to do one more and then we're going to take a little breather, okay?
We do like 90,000 more.
Oh, we will. I think there's like 20 questions. Yeah. Keep repeating it. Okay. relative motion. We're on number 4 here. So this time we have our bearings exactly the same. Then we have our distance. So when I see these at exactly the same, I know that our CPA is 0. That we are on a collision course. But we want to know how fast that collision course is going to happen. What's our speed of relative motion? What's the time of CPA? All that. So let's plot it. 0, 7, 0. And it was at 11 miles, so in between the 12 and the 10. And then it was at 8.5, so 8.5, something like that. I'll get my dividers out. $11. So we labeled this R, and this was at 2006. And then we have 8.5. And this was at 2012. So we have our R and our M. We connect our R and M to get our relative motion lines. And it is along the same degree. So my relative motion line goes through me. So I have a CPA of 0. Red flag. We're going to have to do something. My relative motion line, I don't know why I wrote it out this time. My relative motion line, direction, DRM and SRM. Since it already goes through the center, I don't have to parallel that. I can read it all the way there to get my direction of relative motion is 2, 5, 0, which essentially, no, never mind. I'm not going to go there. Okay, my speed of relative motion, R to M, gives us a distance of 2.5. So that distance there was 2.5 nautical miles.
How come you
So
know
it's-
that scale? Sorry to interrupt. The scale on the left where you got the 2.5, the radar transfer plotting sheet that I just printed does not have that second. It only has like one row
Let me look at it real quick.
scale. Or maybe mine cut it off. Who knows? Oh, maybe it's below. No, I don't know.
Okay, so it cut it off a little bit. Because are you still looking at this, right?
Yes.
Because it's so much smaller, it wanted to maximize the space, so it just cut off half of it.
Okay.
So
But what is that that scale called on that side? Like just in general, how will I always know to use? You just know that it's the second from the left?
no, you want to use the smallest scale for whatever you are doing. So if you had, let's look at an example. Let's see if we have one.
You know, like the Y behind. Like you got two. I understand you like measured and then you moved to that little scale to get the 2.5. I'm just curious, like what the logic is behind 2.5.
So all of our assignments here are going to be on the 12-mile scale. So that's why we're going to use this one here, the 0 to 12, because we first see it somewhere between 8 and 12 miles. And then the second time we see it is going to be a little bit less than that. So you don't want to use the 24-mile scale, because if you do a 12, it's going to be over here. And then if you do it, it's literally going to be half this size, right? And we want it to be as big as possible so that we don't have to be as accurate, essentially. Because if it's zoomed in and your triangle looks like this, you're going to have to be super accurate to get your speed and bearing calculations. So we're blowing it up. You want to use the largest scale possible. So basically, whatever the first bit or range that we have, that tells us which scale we're going to use. So sometimes you're going to use that 6-mile scale, which on yours is below. And sometimes, or I'm going to say 100% of the time for our homework today, you're using the 12-mile scale.
Okay.
Okay. So let's continue that. Okay, so 2.5 miles, it's 6 minutes. So all we have to do is move that decimal over and we get 25 knots as our speed of relative motion. Our CPA is 0. So we don't have a bearing or anything. It's just 0 nautical miles or collision. And then we want our time of CPA. So when is that collision going to happen? We get our 6 minutes from our R to M. Then we walk this over. Okay, so we had 12, 2018, 2024, 2030, 2036. I'm going to say we're a little bit closer to our 2030. So I'm going to say our time of CPA is 2032. And if you want to be even more accurate, this was 2.5. You can half that. So 1.25, if you will. And get a 3-minute mark. 2033. You don't have to do that. Again, your scale here is 3 minutes, but I'm just pointing out how you can divide it up a little bit if you want. Okay, so that is our relative motion line. Now we're going to add in our E so we can plot them, their true course and speed. But first, we're going to take a 10-minute break. So I'll see you in 10 minutes. 8:30. All right. Well, we are going to plot that E. Master the R to M. Now we're going to do E. So kind of easing our way into this triangle, if you will. I'm going to be working. Oh, I haven't shared my screen. I'm going to be working off of the first triangle problem 1 on the problems to do in class. So it looks like this. So we're getting our everything we did before. We had our direction of relative motion, speed of relative motion, CPA, TCPA, and then this is the direction of true motion. So that's the contact. or the target. Target and contact both mean the same thing. They're used interchangeably on however questions are written. So what's the true motion and the true speed of the other target? So we're going to be plotting E. Okay, so let's draw out what they told us. They said we are on course 0, 0, 0. I promise they won't all be 0, 0, 0. But that is our heading line. So I would like to plot that. And we are at a speed of 19 knots. Okay, I'm going to use that, but not exactly right now. At 15:08, you sight a target on the radar bearing 050 at 11.5. 6 minutes later, you see it 048 at 9.8. So let's plot the first one. We have 050 at 11.5. Let's find 11.5. There's 11.5. I'm going to label this R. And that was at 15:08. R. And then 6 minutes later, it was bearing 048. So 48 at 9.8. So let's get 9.8. So here we have M 6 minutes later. So that's 15:14. We have our R to M. So just like the other questions, we're going to connect R and M, and we get our relative motion. So this is our relative motion line. And we want our direction of relative motion. So I'm going to parallel that line back down to the center. And I get a direction of relative motion of 241. Then I want a speed of relative motion so I get the distance between R and M, and then I'm going to convert that to speed. So my distance is 1.7. So I'm going to convert that to speed to say my speed will be 17 knots. So I have my direction of relative motion and speed of relative motion. Then I also want to get my CPA. So I use my 90-degree. There you go. So here is my CPA. My CPA bearing, I'm gonna just write it up here. CPA is going to be bearing 332 degrees at a distance a little over 2 miles, but let's see how much it is. At a distance of 2.4 miles. There's my CPA. Then I want to know my time of CPA. So we have our R to M, which is 6 minutes. There we go. We're gonna get good at adding and subtracting 6 minutes, aren't we? Thinking this in my head. Okay, 14 plus 6, we have 15, 20, 26, 32, 38, 44, 50, 56. So we're in between 44 and 50. So I'm going to call this, maybe here's my 3. I'm going to call this 2 minutes on the 44. So I'll call that 15:46. Okay, I think that's what we did last time. Yep. Now we're going to add in our E. Okay, so, before I add in E, I just wanted to point out, because we have a heading flasher, that this point here is the bow crossing. So when we talk about bow crossing time and bow crossing distance, it's wherever it's crossing our heading flasher. Which is where our bow is pointing, our heading. Okay, can I erase that? So we want to plot E. How do we plot E? Our first step is to parallel our heading. So our heading in this case is 0, 0, 0. So we can move it over to R. So we start at the R and parallel our heading line. Now we're going to go E to R is our direction from E to R. So our heading line was 0, 0, 0, but I drew it in the direction of 180, if you can see that, because I'm going towards R. For some reason that doesn't look parallel to me. Eyes playing games with me. I guess it is. Okay. And then I want my distance. What's my distance in 6 minutes? So my speed was 19 knots. So my own ship is doing 0, 0, 0 degrees at 19 knots. So my distance I've traveled in 6 minutes, we're going to move that decimal point over. Again, we can do that 60D street if we're unsure, but this is why we do it in the 6 minutes, just to make it easy on us. So 1.9 miles is going to be my distance. So let's find 1.9. Okay, 1.9. So here is my E. This distance was 1.9. So now I have my triangle. So I have E to R is me, my own ship. And we can see that down here at the bottom. E to R is my true course and speed, my own ship's true course and speed. So I'm going due north from E to R, due north at 1.9 distance in 6 minutes, meaning 19 knots. So I have me, I have what my direction of relative motion and my speed of relative motion. So now the last thing to plot is E to M. What is that? Direction and speed. That's going to be them, is their true motion and speed. So we're going to plot. I'll use this. E to M. I like to make a big arrow, but you can do whatever you want. And then I'm going to parallel that. We have to do it like this. So that E to M line, that direction is going to be 303. This line is 303 degrees. So my target's true course is 303 degrees. My target's true speed that distance there is 1.9. So my target's true speed is 19 knots. So if I am cruising along here and this guy is cruising along there, he's going to pass ahead of me, bow crossing, he's going to pass ahead of me at a CPA of 2.4 miles. Am I okay with that? Am I not okay with that? That's up to you, or your captain. Not a terrible CPA, but in this case, if 2.4 miles was too close for us, drawing our E to M line helps us identify the situation, right? Who's give way, who is stand on. So I like to go back to our side lights. Remember our side lights, maybe from boat handling? We have our green and our red. We have our green and our red. So if I'm on this boat and I'm looking over here, I'm seeing a red. So that's saying stop, give way. If I'm on this boat and I'm looking over here, I'm seeing a green. You got the go ahead. I stand on, maintain course and speed. So if this is too close to call, then I would have to turn right and get a bigger CPA, and that would end up bending this RML line away from us, giving us a bigger CPA, which we're going to do next week. Okay, everyone get how I drew that E?
I have a question. I get how you drew the E, but I don't know why you had like a parallel line. What was the importance of when you drew E to M, and then you were going to draw a parallel line?
I drew this line.
Oh, okay. Yeah, that line. Yeah.
So that's finding exactly what their E, that's what their course is. So I can find it and put a number on it.
Mhm.
So I know that they're pointing in this direction and I'm pointing in this direction, but I want to know what that actual bearing or what their actual heading is. So I drew the line, but I have to parallel it to the center so I can get a number to it.
Why does it have to be from the center and not from where it was before?
So if I draw this line out to the side, it's
Mhm.
crossing the outside of the circle
Mhm.
at 0.55 or something, or 355. And that's pretty close to due north. And this line is not due north, right? This line is pointing west northwest.
Mhm.
So that's just how this radar plotting sheet works.
Okay.
Is in order to get a measurement of a line, you have to start it from the center.
Okay, so it doesn't really have anything to do with like that is your own location.
No,
It's just getting it from the center.
it's just measuring that line, and that's how the radar plotting sheet works. To measure a line, it starts from the center.
I see. Thank you.
Yeah.
It all makes sense, but I'll probably need to do it 89,000 more times.
Okay, okay. Well, let's do it again. A lot of examples. I feel like it makes more sense if we have examples.
Definitely more examples. Yeah, I'm with you.
Okay. So this one, we're thinking outside the box here. And so I'm looking at number 2, problem number 2. Our course is 123 true at a speed of 22 knots. So we are not on the due north track. We are changing it up. So our triangle is going to look a little bit different than how it's looked in all of our things, but we'll see it. You sight on the radar a target. 6 minutes later, you spot it again, plot. So I start with my heading flasher. I am headed at 123. I always do this. So this is my brother-in-law's office, and he is like 6'5", and I'm 5'2". So I feel like a little girl at this. I feel like a little person at this desk. I'm so small. Anyways, because I can't see it. I can't see my lines when it's this way because I'm too short at this desk. Anyways, okay, this is my heading. This is me. Let me write this in a second. Okay, so own ship. Own ship is 123 degrees at 22 knots. That's what I'm doing. Then I get 2 blips on the radar. I get 1 blip on the radar. 6 minutes later, I get the other. First one is at 188 at 10.2 miles. So 188 at 10.2. And what do we label this one? R.
ML. No, just R. Sorry.
R. So we're going to label this R. And that was at 1300.
And just for my own benefit, R is the designation of the first contact of a given target. M is the second contact of the same target.
Correct.
Thank you.
Okay, so at 289, I might have done this wrong. 289, oh, it's here. we have a distance of 8.3. Okay, and we labeled this one M. And that was at 1306. So we have our R and our M. And then we have our own ship. So we connect R and M. And we get our relative motion line. So we can see it looks a little bit different, right? But it's the same steps that we've been doing. So our direction of relative motion and our speed of relative motion. To get direction, we parallel this line back to the center. And our direction of relative motion is 0, 0, 3 degrees true. And our speed of relative motion.
Why did you add the true?
Oh, that's just a habit on doing other things.
Okay.
Sorry.
No, that's okay. I just hadn't seen the true before.
Yeah.
Yeah, Captain Bree, do you normally work in true on radar as
Yes.
opposed to magnetic?
Yes.
Okay.
Now, I'm going to say yes to that because it keeps it simple. But if you have a stabilized radar, which you most likely do, you have to have a compass input. So is that compass input from your GPS? Is it from a gyro? So it might be in gyro. It might
I was
be,
just gonna, that makes sense now with the gyro. Okay.
it might be in whatever,
Yeah.
you have inputted.
Okay, cool. I got you. Thank you.
Okay. So R to M distance, sorry, I'm a little bit over here, is 1.9, meaning our R to M speed is 19 knots. Then we get our CPA.
Is SMR supposed to be SRM?
Yes.
Okay.
Okay.
I'm not trying to
Did I
nitpick.
tell you I was in Texas and it's like 11 o'clock at night?
Oh,
No excuse, no excuse. Okay. So 90-degree angle to our R to M line to the center. This is our CPA. Oops. Draw it all the way out. So our CPA has a bearing of 274 at a distance of 0.9 nautical miles. Time of CPA here's our 6, 12, 18, 24, 30, 36. So we have 6, 12, 18, 24, 30, 36. So we can say our CPA is 1332, 1331, 1332, something like that. Okay, now we're going to plot our E to get our two more things. The two things that we want is our E to M, which is my target's course and speed, true course, true speed. Okay, so I need to plot my E. I'm going to parallel my heading line. So my heading line was 1, 2, 3, right? I'm going to parallel that. I'm running off my chart here. Parallel my heading line to my R. Then I'm going to draw a line back. So that's my direction, but I need to figure out where my E is so I can go from E to R. In 6 minutes, my speed is 22 knots. So in 6 minutes, I would have traveled 2.2 nautical miles. So I'm going to get 2.2 and go from R. Distance here is 2.2. So here is my E. So I have E to R. This is the direction of 1, 2, 3 at 22 knots. R to M is the relative motion line. So E to M is them, is going to be their line. I'm going to parallel that up. So this is them, right? They're heading this way, E to M. Maybe I'll do it like that. E to M. And to get the value of that heading is 0.72.
Wait, is the boat them or us?
The boat is them. Where's my other boat?
Okay.
That's us.
Okay. All right. Now I got it. I got it. Okay.
Their speed, E to M.
The boats helped a lot.
Okay, good. Is 2.1. So if that distance is 2.1, 6 minutes, their speed is 21 knots. So that's them, and this is us. So who is give way? Who is stand on?
They are stand on.
Correct. And if nothing changes, are they going to pass ahead or behind us?
I want to say they're going to pass ahead of us.
Nope. Their
Oh, wait.
relative
I'm sorry.
motion
Yeah, our
line-
speed. I got it. Yeah.
So we have no bow crossing, right?
Right.
It's not crossing our heading flasher. it's crossing our stern.
Mm.
But it's only passing our stern by 0.9 miles. And if we are the giveaway, we don't want to be crossing ahead of where this is going to happen, right? We don't want to pass ahead of a vessel that we have to give way to.
Wait, where did the little circle up by the center come from? I completely missed that. Okay.
That's my CPA. For some reason, I drew it as a circle. There we go.
Ah.
CPA.
Okay. All right. Cool. Okay. Wait.
Okay.
Okay. And so that's how you ascertained it was passing your stern, not your bow, was because of the proximity of that. Okay.
It was because the relative motion line
Yeah.
was on the stern
Aft.
side of
Yeah.
the center. This is the center of the scope. I know it's
Yep.
so close.
No. Now it makes sense. I got it now. Okay. Cool.
Okay. So on this one, you can see that it looks a little different, but it's all the same steps that we've been doing, right?
Yeah, there's still something not clicking for me in the placement of the E and arriving with like a CPA. Yeah, I definitely need another exercise.
Okay. Okay. Let's keep chugging along here.
I will say, Captain Bree, on an up note, in all my years, I've never heard anybody explain right of way with the red light, green light, stop, go thing ever. That was perfect. That was like, I'm going to use that every day with students from now on.
Captain Karen does that in our boat handling class.
That's, I don't know how I never heard anybody ever use it like that. That's so fantastic.
Yeah. Red and green. Okay. Number 3. So again, we are not at our 000 heading. We're at 220 at a speed of 12 knots. We have a bearing, and I can see from these two bearings, our CPA is going to be 0 because our bearings are the same. And then we're going to figure out the rest. No, we have time. It's only 9. Okay. Wait. Yeah. Okay. Sorry. What am I doing here? Okay. We are on course 222.
We're doing 3.
Number 3.
Okay, I see it's 000, but maybe I'm looking at the wrong thing. Paper.
So you're looking at the homework.
Oh, what are you looking at?
This one's homework. So this one is just called First Triangle, and it's our in-class practice.
Oh, okay.
Okay. So 170. So my own ship is 222 degrees at 12 knots. Then I have some blips on the radar. So we're going to plot that at 170 at 9.4. And then at 170 at 6.4, 2, 4, 6. So we had and this was at 0448 and our 6.4 is our M, and that was at 0554. Excuse me, 0454. So we have our R and our M. We could make them dots. I don't know why I've been making, I think I'm just trying to make it more visible for you guys with the whole circle thing. But you can just do a dot. Okay. We connect our R and an M. And we have a CPA of 0. Collision. Don't like it. Our RML, or direction of RML, speed of RML. Our direction is 350. I didn't have to parallel this one because it's already crossing through the center. Our speed of relative motion is going to be 3 knots, or the distance here is 3.0 nautical miles. So our speed of relative motion would be 30 knots. So it's happening pretty quickly. Our time of CPA so we have 54, 0500, 0506, 0512. So I would call our CPA was 0, but our time of CPA is 0507. Okay. And CPA, relative motion. Okay, now we're going to find our plot our E so we can find what their true motion is. Okay. So our first step to plotting E is to parallel our own ship's heading 222 from R. Let me erase this real quick. So I plotted away from R, and then I want to get my distance in 6 minutes, which would be 1.2, because I'm going 12 knots. So here is my E. So E to R E to R is my own ship. So I am headed in the direction of 222 at 12 knots. E to M is them, what they are doing. So we're going to connect E to M. I don't know why I can't do this tonight. Oops. I shouldn't have drawn it that far. Okay. E to M is them. And I want to figure out what their actual heading is. So I can write in the number. Let's call it, so target course is 325 degrees. Target speed is we're going to measure E to M. Their distance there is 2.4. So their speed is 24 knots. So let's see what's going on here. So we have we're relatively moving slow. These guys, we're moving at 12 knots. They're moving at 24 knots. And we have a 0 CPA. So who is the stand-on vessel?
Would it be the green, the teal boat? Them.
No, it would not.
Oh, I'm sorry. Stand on.
Stand on is us. We get to maintain course and speed.
But isn't it always
And
like
they turn to give way.
okay?
What about always?
I like not trying to, like with the plot, but because like so I've like learned in Captain Karen's class, because they'll see red, so that means they have to stop, and then we would go.
Yes.
Not mattering about like, and like not with like navigational rules either, if like we're anchored or what kind, like, but just like in general, because like we're to the right of them, then we
Yes.
are.
So we are traveling at 12 knots,
Mm-hmm.
right, at this course, and we see a green.
Mm-hmm.
So we continue with our course and speed, and they have to give way to us, meaning that they're going to turn.
Okay, so it doesn't matter. I guess what I'm saying is like anytime after we finish one of these plots, I mean, anytime whoever is on the right is always has the right of way, correct?
Correct.
Okay.
If risk of collision exists.
What's that?
If risk of collision exists.
Okay.
Right. So we had one plot where our CPA was like over 2 miles.
When the CPA is 0.
Maybe collision doesn't exist. In this case, our CPA is 0. So risk of collision definitely exists.
Okay. I guess why I asked that too is like, it almost seems like a trick question, but from learning that who's on the right has the right of way, because then the other ship sees red. So that's why I'm like, wait, isn't it always that? But only if the CPA is 0, if there's a risk of collision. Okay.
Yes. So when we get to week, I don't know, 6 or 7 in this class, we're going to plot this thing with multiple targets. And we
Oh,
have to decide on all 3 of those targets, which one has risk of collision.
I see.
And if we maneuver for that one, how will it affect our relative motion line on the others?
Okay.
That's where we're going, but we're just doing it slower.
Thank you. Thanks for going slower.
Yeah. Okay. Let's do another one. Problem number 4. We are 020, 15 knots, 040, and 044. So let's plot this. Zero to 0. There is our heading line. So I'm going to say my own ship 020 at 15 knots. Then I'm going to plot my 8 o'clock. I sight a target bearing 040 at 9.1. Plot that. So this is R, and that was at 0800. And then at 0806, it is 44. At 7.6. 8, 7.6. So this is our M, and at 0806. Clean this up. Okay, so we're going to plot our R to M. Parallel that over. Okay, so this is our relative motion line. Our direction of relative motion, I paralleled it over so I can get a measurement, was 202. Our speed of relative motion, okay. Speed of relative motion line, about 1.5. So my distance is 1.5. That would give me a relative motion of 15 knots. For my CPA, I see right or a right angle to my relative motion line. This is my CPA. Its bearing is 112 at a distance of 2.9 miles. And I want a TCPA. So this was 6, 12, 18, 24, 30, 36. I'll call our CPA 08, 32. Okay. So now we did everything with our R to M line. Now we want to plot E, right? That is our next point to get the target's true course and the target's true speed. Okay, so we're going to plot E. So we use our own ship's heading line. And we go from R back. So it is right on our relative motion line. So they're either going with us, going opposite of us, or not going at all. So we'll figure out that by putting our E in. So we are going 15 knots. So we'll do 1.5. And 1.5 is right where M is. So our E and our M are at exactly the same point. So our triangle is not a triangle. So we'll look at each vector individually here. So R to M is the relative motion. E to R is us, right? We are going this direction at 15 knots. E to R is our own ship. So E to M is them, but E to M is not a line on here. So what does that mean? That means that E to M is not moving. E to M is dead in the water. E to M is a buoy. Whatever this target is not actually moving. I have no true vector. I have a relative vector, right? R to M, which is opposite of me, essentially. And my E to M is nothing. E and M are exactly the same. So let's, as we are processing that in our heads real quick, let's look at this video again. We have relative motion, and then we have true motion. So those relative motion lines disappeared when we switched to true because there is no line for true. These are dead in the water. They're not moving. Hold on, it'll go back. Okay, here's my relative motion line again. Those things that were dead in the water are a reciprocal course of what I was doing and my speed. I feel like it's easier on the smaller ones. There we go. You guys see how that's the relative motion line? And then that's our true line, or our true vectors, meaning that E to M is nothing. It's not a line. So when we go back to our plot, and our E and our M are the same dot, that means it is dead in the water, not moving. It's a buoy, basically, or an anchored boat. It's not moving. Did I lose you guys? How are you guys doing?
You didn't lose me.
Okay. All right. Any questions so far?
On the video that you just were showing us, I think you mentioned this earlier, but I already forgot. So the RMLs for those buoys, the dead in water, why were the line, like why were they like north of them? Like why are the lines up there?
So on here, my heading flasher, my heading is this direction.
Okay.
So their relative motion line, if I am going this way, relatively, it's just passing me behind me, right?
Okay.
Relatively, it's moving that way. If I'm moving this way and it's not moving.
Uh-huh.
So it's opposite. Its relative motion line is opposite of what my heading and speed is.
I see.
So when we go back to,
and how do we know that we just on this video that we are moving that way? As it was on the side, like how would we know where the boat is moving?
So
just because of the line?
My heading flasher is pointing in this direction, 190.
Okay.
So I have a heading up here, 190, and my heading flasher is the line that goes directly all the way to the end.
Oh, so okay, so that's how you know that's the heading flasher and not the other way around.
Correct.
Not to state the obvious, but I'm just curious, like, how would you read that? How would you
Yes,
know
and
all the way?
Typically you're going to be looking at a screen that is from the center. So it's like any line from the center. This is offset, which you're typically not going to see. Just because I wanted to see more targets in the scope when I was making this example. But I should have just kept it centered. I don't know. It's offset, which makes it confusing. What was I gonna do? So when we're looking at R to M, so this is us. We are headed this direction, right? This is our own ship. So R to M is our relative motion line, where E to R is our own line. So you can see they're exactly reciprocals. So E to R is me. E to R. And then if I switch to relative motion, that line's going to be passing alongside me as I travel. Okay. So that is what we have for today. For the homework, you could answer all of one. There gets to a point, I think, maybe towards the end of it. Yes, where it starts talking about CPA. and changing your course, that's going to be next week. So I would do up to where it says you decide to change course. Does that make sense? So do the problems,
That's
but
the
you don't have.
That's next week's homework?
This is actually this week's homework, but next week we're going to be doing the CPA stuff. So we'll do that next
Okay.
week.
Okay.
But still remember to submit it on Canvas so I can give you guys credit for it. Again, it's just the date thing. So and then so you could practice with these, and then if you want 90,000 more, these the first 10, I think, let's see. Yeah, the first 10 are just doing that R to M line. And then the second 10 are doing plotting the E. So that's just, yeah, getting that muscle memory. So I guess this one, I say it's optional. You don't have to do it if you're feeling comfortable with the actual homework, but I wanted to give you extra practice.
And that actual homework we did not do yet in class. We will do that on our own. But to submit, we just put a date. We don't submit like that with charts.
Correct.
Okay.
So for the homeworks, I'm just saying submit the date that you do it. So kind of honor system here. So the more you do it, the more comfortable you'll be. Not next week, but the next week, we're going to start the class with a quiz. So that quiz will be just like this. Will be, here's your course, here's your speed, here's a target, range and bearing, here's a target, range and bearing, what's, relative speed, relative direction, time of CPA, target true course, target true speed. So same thing that we've been doing, but the more you practice and do the homework, the better you'll be at the quiz.
And then the extra charts that you have online, those are for us to like print and do just for like extra work.
Yes.
Or practice, I should say.
Yeah. So the more you do it, the more comfortable you'll be.
Okay. Thank you.
Cool.
Yep.
Thank you. See you next week.
All right. You guys have a good one.
Sabrina, no sailing tomorrow.
Okay. Sounds good. And travel safe, Captain Bree, back to California.
Thank you.
Yeah.
I'll
you
be
too.
back home.
Okay.
All right. Bye.